While reading the title of this paper, you probably asked yourself, what does coherent propagation mean? Well, according to classical mechanics, an object can be considered as a particle or as a wave, two intrinsically conflicting quantities. A particle is something localized, something whose position in space-time can be determined absolutely. It's this continuous object. For example, you won't find anybody claiming to be able to cut an atom like a pizza. On the contrary, a wave is something delocalized, something which extends over a region of space-time. A wave is continuous and you can tune its amplitude as you wish. However, according to quantum mechanics, things get really mixed up. If we believe Einstein, then waves behave like particles. However, if you believe the hypothesis of de Broglie, a single particle can also behave like a wave. Really weird. So how can we demonstrate experimentally that a particle is behaving like a wave? Simple, we just let it interfere. But what does interference mean? Well, as a child, you probably noticed that when you throw a stone into a pond, you generate waves. Now imagine that these meet a wall with two openings, each acting as a secondary source of waves. If you look at what happens to the water far from the wall, you can see interference taking place. At some positions, the waves arrive together and combine to give more water at that position. In other places, they combine to give less water. This results in the familiar sinusoidal pattern we associate with interference. Now imagine that you throw flowers, one after the other, towards the same wall as before. On a screen positioned on the other side, you'd expect to see the flowers only behind the openings, a very different distribution to the water waves. What if we now repeat the flower experiment, but this time we use a quantum flower? Here, all we mean by quantum is that we're not allowed to see which of the slits the flower passes through, like here where the cloud covers the slits. Now what you find is the intensity distribution that looks just like the waves we saw before. This means that the flower is coherently propagating through the openings. Quantum physicists will claim that your flower is now delocalized. If you want to build a matter wave interferometer, you need three ingredients. First of all, a source of quantum flowers, secondly a wall with two or more openings, and finally something to count each of the flowers on the other side of your wall. Our quantum flower is a thylocyanine molecule. Individual molecules are introduced into the gas phase by shining a tiny focus laser onto a glass window coated with the molecules. Thylocyanine is good because when we illuminate it with a laser, it will fluoresce. By collecting this fluorescence light with a microscope, we can count single molecules on a screen behind our wall. This means we can image the interference pattern. As for the openings, they're normally produced in a nanotechnology center, as you need tiny regular structures. Let's suppose we want to distinguish two interference fringes separated by 1/40th of a millimeter on a screen placed half a meter downstream. If you consider a thylocyanine flying at 170 meters per second, you need a slit separation of almost 100 nanometers, which is about 1,000 times smaller than the diameter of your hair. But hang on a second, can you find a nanograting for free in nature? Well, the answer is yes. This is a picture of an Amphipleura Pellucida skeleton, a type of marine alga. This alga shows a nanometer-sized periodic architecture in two directions. In particular, we can see that there's a 205 nanometer hole separation along the x direction and 120 nanometer pore opening. Now what happens if we send our molecules one after the other through the alga? Can we see interference? The answer is yes. We managed to delocalize a particle through the pore of a biologically grown nanostructure. Now this is really cool, but you might be thinking, what can we learn from this? In order to answer this question, let us focus on the diffraction intensities marked. We take a picture of the alga and then using the Kirchhoff-Fresnel diffraction integrals, calculate the molecular intensity distribution we see. Then we compare this to what we see in our experiment. Two things are clear. First of all, the theory predicts a two-dimensional interference pattern, but we only observe a one-dimensional pattern. There is a simple explanation for this: gravity. While the molecules fly from the source to the detector, they fall in the Earth's gravitational field. As a result, different velocities will contribute to the same spatial region along y, and the pattern will be smeared out. Secondly, and this is good news, the interference pattern is preserved along the x-axis. But if we compare the theory with the data, we notice something more. In the theoretical simulation, the high interference orders are almost missing. There must be something else going on here, so what's the trick? While flying through the alga, single molecules experience an interaction potential with the surface of the pore. This interaction is described by the van der Waals potential. From an experimental point of view, this interaction can be mimicked by an effective reduction of the alga opening. This results in a larger population of the high interference orders. If we repeat our simulation by iteratively shrinking the opening of the pore, we can estimate an effective reduction as high as 83 nanometers. Alternatively, we can repeat the simulation, adding a dephasing term to the integral, and we can estimate the interaction constant between the thylocyanine and the inner surface of the alga.